Good day, everyone. Welcome again to Modeling Methods in Mechanical Engineering. And today we're going to continue our discussion on partial differential equations. In particular, we're going to talk about what happens with the method of separation of variables if you have more than one non-homogeneous condition. So far, we've established that the criteria for separation of variables to be applicable to a problem is that the problem is linear, it's framed in an orthogonal coordinate system. And there's only one non-homogeneous condition. The rest have to be all homogeneous. So what happens if you have two, for example, non-homogeneous conditions? So let's go directly into how to address that problem. So this is modeling methods in ME. And this is, so what happens if there is more than one non-homogeneous condition? What happens is that separation of variables does not apply directly. Instead, use superposition plus SOV, plus separation of variables. So it's a combination of two things that we need to do. So I'm going to give you a simple example to show you how to address this in general, and this again can be generalized to problems of any dimensions and with as many non-homogeneous conditions as you impose. So let's say that, for example, we have a problem like this. That's what we have been solving so far, and x and y, and then the problem is a rectangle that is size L by L, and internally we are solving for the equation of Laplace of t equals 0, where t is a function of x and y only. And let's say that on this wall we have t equals 0, on this wall we have t equals 0. Let's say that on this wall we have t equal 1, and on this wall we have t equal 1. So we have two non-homogeneous conditions. So the governing equation can be formulated as the Laplace of t equals 0, which, remember, is simply d second t dx squared plus d second t dy squared equals 0. So it's the same thing, just in short form. Where the boundary conditions are posed as temperature at x equals 0, comma y. So at x equals 0 will be the left wall is equal to 0, while the temperature at x equal L, comma y is equal to 1. So as you can see, in the x direction is non-homogeneous. So they're both first kind. You can have a combination of first kind and second kind, or first kind, third kind, second kind, third kind, whatever combination you can envision. Likewise, in the y direction, we have x comma 0, that's the bottom wall, is equal to 0, while t at x comma small l is equal to 1. So here in the y direction, you have non-homogeneous conditions. So separation of variables is not applicable because you cannot form an eigenvalue problem in any of the directions. So the key to this is, let's make an arbitrary decision and let the temperature of x and y be equal to some temperature 1 of x and y plus temperature 2 of x and y. This is what we call superposition. We're superimposing two possible solutions. And then we're going to make an assumption. So if the Laplace of t is equal to 0, then, well, this is not an assumption, then the Laplace of t1 plus the Laplace of t2 will also be equal to 0, since we're assuming that the temperature is broken up into T1 and T2, then And that's possible because the problem is linear. Remember, the principle of superposition says that you can construct solutions out of existing solutions. So if T1 is a solution and T2 is a solution, T would be a solution. It's a combination of the two, a linear combination. So if T is T1 plus T2, then the Laplace of T is also the Laplace of T1 plus the Laplace of T2. It's a linear operator, and therefore you can break it up like that. So the next is the assumption. So we are going to arbitrarily let the following. So if the Laplace of T1 plus the Laplace of T2 is equal to 0, I can very well say that the Laplace of T1 is equal to 3, and then the Laplace of T2 is equal to minus 3, and that satisfies, but that doesn't help in anything. So I'm going to arbitrarily say that the Laplace of T1 is equal to 0, and therefore, I'll break this in half here, and therefore, the Laplace of T2 should also be equal to 0. This one plus this one is equal to 0. And now I'm going to also break up the boundary conditions. So if you look at the boundary conditions, I'm going to try to squeeze this here. So the Laplace, so T is T1 plus T2. So T1 plus T2 is equal to 0 at x equals 0. So basically, T1 at x equals 0, comma y is equal to 0. And therefore, T2 at 0, comma y should also be equal to 0, because this plus this one should equal T. Now, if T1 at x equal big L, I'm going to set it up to be 0 also. Then T2 at L, comma y, then should be equal to 1, because 0 plus 1 gives you 1. And likewise, if T at x, comma 0 is equal to 0, T1 at x, comma 0 is equal to 0, then T2 at x, comma 0 should also be equal to 0. And if T1 at x, comma small l is equal to 1, then T2 at x, comma small l should be equal to 0. And now we have two separate problems, each of which is eligible for use of separation of variables. So solve for T1 using separation of variables. And then solve for T2 using separation of variables. And we know how that process goes. We've actually solved problems that look just like this. And I'm not going to go through the entire formulation, but we know that T1 of x and y, so we form an eigenvalue problem in the x direction and a non-eigenvalue problem in the y direction for T1. And then we end up with the following solution. Summation from 1 to infinity, n sine of lambda n x, sine hyperbolic of lambda n y, such that a sub n is 2 times 1 minus 1 to the power of n divided by n pi sine hyperbolic of lambda n l, and lambda n is equal to n pi over L. So this is the solution of problem T1. Likewise, we do it for problem T2. T2 will then be a problem whose eigenvalue problem will be in the y direction, and the non-eigenvalue problem will be in the x direction. And this will yield a solution as an infinite series from 1 to infinity, Bn sine hyperbolic of beta n x sine of beta n y. So now you can see that the eigenfunction is in the y direction, such that Bn is equal to 2, 1 minus 1 to the power of n, n pi sine hyperbolic of beta n L, and beta n is equal to n pi over small l. So this is the solution for T2. eigenvalue for T2. And then ultimately, all we have to remember is that the solution that we're looking for, which is T of x and y, is simply equal to T1 of x and y, which is given by this, plus T2 of x and y, which is given by this other series. And that's it. That's as simple as it gets. Now, if, for example, you can continue to generalize this, if this problem was in 3 dimensions and you had 2, then you solve a 3-dimensional problem that would have a double summation. If this problem had more than 2 non-homogeneous conditions, so if the original conditions had 3 non-homogeneous conditions, it can again be first kind, second kind, or third kind, then you will break it up into T1 plus T2 plus T3 and do it exactly the same way. So this is how superposition works. Now, what if the non-homogeneous condition, one of the non-homogeneous conditions, or even the only non-homogeneous condition, so what if the governing equation is non-homogeneous? Okay, you can have non-homogeneous boundary conditions, but also the equation could be non-homogeneous. So, for instance, when we have steady heat conduction with steady state heat conduction with internal energy generation, UG triple prime. So it's energy per unit time per unit volume. That's what goes in the equation. So steady heat conduction, remember, goes as the divergency of the conductivity times the gradient of the temperature. This is the heat flux. This is the divergency of the heat flux is plus UG triple prime. This generation would be equal to rho C times the temperature derivative with respect to time, but in this case it's steady state, so this is equal to 0. So where UG triple prime is energy per unit time, so watts per unit volume, watts per meter cube, so that's dimensionally consistent. Now let K and UG triple prime be constant, and this would be for purpose of illustration. UG triple prime doesn't need to be a constant, but for the purpose of illustration, then this will go down to the Laplace of T plus UG triple prime divided by K is equal to 0. And then we can just summarize this as something called Q0. And this right here is no longer called the Laplace equation. So when you have the Laplace of a field variable plus a constant, we call this a Poisson equation. The Poisson equation. So let's see how do we resolve that. Let's look at an example where we have, let's say again, a rectangular domain X and Y, and again this is L, and then internally here we have the Laplace of T x comma y plus some Q0 is equal to 0, so we have a generation term. And let's say that the temperature here is 0, the temperature here is 0, the temperature here is 0, and the temperature here is 0. So all homogeneous conditions. That is not necessarily a requirement. You can have whatever combination of homogeneous and non-homogeneous. You're going to have to use superposition. And you can have whatever combination of first, second, or third kind conditions. So just for illustration purposes, this is where we are. So again, the governing equation looks like this. The Laplace of T, which is the second derivative of T with respect to x squared, plus the second derivative of T with respect to y squared, plus some constant Q0 is equal to 0, where the boundary conditions are given by temperature at 0, y is equal to 0, temperature at L, y is equal to 0, temperature at x comma 0 is equal to 0, and temperature at x comma small l is equal to 0. So this is in the x direction is first kind homogeneous, and in the y direction is first kind homogeneous. So x direction, y direction. Now, and although we had stated that the method of separation of variables applies as long as you have a single non-homogeneity, which is what appears to be the case here, it would not apply directly because the non-homogeneity has to be in the boundary conditions. There's no way that we can solve this problem by forming two eigenvalue problems in the x and in the y direction, because the separation of variables will not work out that way. So, what is it that we need to do? So now we have to play a trick. The trick is also with superposition. So the way this works is, even though there is only one non-homogeneous condition, in this case it's not a condition, it's the governing equation, SOV does not apply directly. Instead, try a superposition. So we can superimpose T1 plus T2. That's a way to do it. An easier way to do it in this case is to try, well, let's make T of x and y equals to, instead of calling it T1, let me call it theta. There's no difference, but I just want to be fancy and call it theta. And phi, the second superposition, I'm just going to make it a function of x. Right? So, and that is the one that is going to carry the Q0, the non-homogeneity in the governing equation. So, the governing equation, which remember used to be the Laplace of t plus Q0 is equal to 0, is now the Laplace of theta plus the Laplace of phi, but the Laplace of phi is, since phi is only a function of a single variable, Laplace doesn't make any sense. It's just simply the second derivative of phi with respect to x squared plus Q0. So this is equivalent to the Laplace of phi because phi is a function of a single variable. So this is a new governing equation. And now I am going to I'm going to break this up into two. I'm going to let theta be just the Laplace equation. And then what's going to happen is that if I let theta be equal to 0, and then this 2 would just be equal to 0. Alright, so that's simple enough. This one plus this one should be equal to 0, according to this superposition that we implemented. And now let's see what happens with the boundary conditions. Now, let's go back to the original boundary conditions. They were all 0. So basically theta plus phi has to be 0, theta plus phi has to be 0, theta plus phi has to be 0, and theta plus phi has to be 0. So if we let theta at x equals 0, comma y be equal to 0, then phi at 0 should also be equal to 0. So theta plus phi is equal to 0. If theta at L, comma y is equal to 0, then phi at L should be equal to 0. Because t at L, comma y is equal to 0. If this was different than 0, we just make this one 0 and this one something different than 0. Right? So we pass the non-homogeneity to phi. Since this is just an ordinary differential equation, it really doesn't matter. What happens with the other two conditions? Theta at x, comma 0 plus phi at x should be equal to 0. So that means that theta at x, comma 0 is equal to minus phi at x. There's nothing that we can say for phi at y equals 0 because phi is not a function of y. All we know is that theta plus phi should be equal to 0. So theta should be equal to minus phi. And the same thing goes for theta at x, comma L. that should also be equal to minus phi, because theta at x comma L plus phi at x should be equal to 0 according to this equation. All right, so there's no conditions in the y direction for phi, because phi is only a function of x. Now, basically, what's going to happen is that you need to solve for this problem first. This is an ordinary differential equation, very simple to solve, and then use that as a boundary condition for the next problem. So we need to solve for phi of x to be able to solve for theta of x and y. And the way it goes is, if we want to solve for phi of x, remember the equation we're solving for is this very simple ordinary differential equation, second order, but there's no first order, there's no zeroth order, there's just a non-homogeneous term. So there's no first derivative or zeroth derivative of phi. So this is actually quite simple. All we need to do is integrate twice q0 to get to phi. So let's do that in a couple steps, but this is a pretty simple process. So the way it goes is that if d second phi dx squared is equal to minus q, or minus q0, then the phi dx should be equal to the integral minus q0 dx. That means that the phi dx is equal to minus q0x plus some constant of integration c1. Furthermore, then phi of x should be equal to the integral of minus q0x plus c1 dx. And therefore, phi of x should be equal to minus q0 x squared over 2 plus c1x plus c2. All right, so this is general solution. I'm going to use blue to denote that it's not done. We have these two boundary conditions. So phi at 0 should be equal to 0. That means that minus q0 times 0 squared divided by 2 plus c1 0 plus c2 should be equal to 0. From here, we can very easily see that c2 will be equal to 0. This one is sort of final. And the second condition is phi at L is equal to 0. That means that minus q0 L squared over 2 plus c1 L, and there's no c2 anymore. And from here we get c1 equals to q0 divided by L over 2, or times L over 2, sorry. That's c1. So the final solution, once we plug in c1 and c2 into this, is that phi of x is equal to q0 x over 2 L minus x. Okay, I've already taken x as a common factor, and that's what we end up with. So it's just some quadratic function, some parabola in the x direction. Again, that's arbitrary, because we said originally that we were going to superimpose, we're going to assume that t is theta x and y plus phi of x. We could have said phi of y, and this would have worked exactly the same way. It's just this function would have been a function of y. So it works out this way. Now we need to solve for theta. And theta of x and y has the following governing equation. The Laplace of theta is equal to 0. And the following set of boundary conditions. Theta at 0, y is equal to 0. Theta at L, y is equal to 0. So this is homogeneous. So this is x direction homogeneous. And theta x, 0. And theta at x, L. This is minus phi of x. And this one is minus phi of x. So we have the same condition on at y equals 0 on the bottom plate and on the top plate, and this is the y direction is fully non-homogeneous. All right, so separation of variables still doesn't apply because we need this problem to be a single type of homogeneous condition, or single non-homogeneous conditions. So basically, apply superposition again. And that is, let theta of x and y be equal to theta 1 of x and y plus theta 2 of x and y. And we're going to solve this problem exactly the same way we just solved the problem that had two non-homogeneous conditions. The way it's going to work, again, is that the first problem is going to have the Laplace of, so if the Laplace of theta is equal to 0, then the Laplace of theta 1, we're going to let be equal to 0. And then the Laplace of theta 2 should also be equal to 0. This plus this one gives you 0. And the boundary conditions are this one stays, 0, y is equal to 0, and therefore theta 2 of 0, y also equals 0. If theta 1 of L, y is equal to 0, then theta 2 of L, y is equal to 0. If theta 1 of x, 0 is equal to minus phi of x, then theta 2 of x, 0 then will be 0. So theta 1 plus theta 2 is equal to minus phi of x, and that satisfies. And finally, if theta 1 of x, small l is equal to 0, then theta 2 of x, small l should be equal to minus phi of x. And now I have two problems, each of which I can solve using separation of variables. So solving for theta 1 and theta 2 using separation of variables leads to the following. So theta 1 of x, y is a summation from n equal 1 to infinity of Cn sine of lambda nx sine hyperbolic of lambda n times y minus l, such that Cn is equal to 2 over L times the integral from 0 to L phi of x sine of lambda nx dx times 1 divided by the sine hyperbolic of lambda nl, such that lambda n is equal to n pi over L. So this is a solution for phi 1, where this is a constant of integration, which we can integrate analytically very easily. Remember, this is a quadratic function, so we have to do integration by parts, or we can just let MathCAD do it for us. And similarly, theta 2 of x, y would be the summation from n equal 1 to infinity of dn times the sine of beta nx sine hyperbolic. So see, the eigenfunction is in the x direction in both cases, because the x direction is the homogeneous direction, and this will be beta ny, such that dn is equal to 2 over L times the integral from 0 to L of minus phi of x sine of beta nx dx, which is the eigenfunction, times 1 divided by the sine hyperbolic of beta n small l, such that beta n is the same eigenvalues. So this is theta 2. And that's it. And recall that then we can form the temperature of x and y as theta 1 plus theta 2 plus phi of x. And these solutions are already given by this set of equations. So this is how superposition works, and you can apply superposition in whichever. Remember, these are all arbitrary decisions. We essentially said at the beginning of the problem that we were going to let the temperature be equal to a function of x and y in a function of x. We could have said function of x and y plus a function of y, or even a function of x and y plus a function of x and y, and try to come up with a solution, a particular solution that matches that, which should be easy to find, right? A solution that satisfies the Laplace of phi plus q0 equals 0 with no boundary conditions, right? And then pass those boundary conditions over to phi to theta. And that will be a lot more complicated than just picking up a one-dimensional function like this. So that's it. As I said, there's many different combinations which we can implement superpositions so that as to make separation of variables work properly or work. And we'll see this also in transient problems in our next lecture. So thank you for your attention, and I will see you next class.